Yay! Hello, lovely humans! Jen Foxbot here. In this video, we are going to actually dig into a course on machine learning. So, full disclosure, I took Andrew Ng's course on Coursera a couple of years ago. Ha! Time. Wild. And I'm pulling all of this from that course. I'm going to make some caveats. I probably will skip a few things. And I'm going to assume that you don't know as much about calculus as I do, so I'll probably explain things in a little bit more detail. But if you want to learn the nitty-gritty details of machine learning, the mechanics behind machine learning, I would highly recommend that course. Okay, so machine learning. We're going to call this 101, and we're probably going to do 101 A, B, C, D. We'll see how long the 101 gets us before we get to 102. All right. So the first thing that I want to start out with is that there's a few different terms that kind of get smushed around together and used kind of interchangeably, but to define them, so artificial intelligence, or AI, don't get me started on this terminology. I'm not a big fan. It's not intelligent. We'll leave it at that. But it is what we're calling it at the moment. So there's a field of AI, and then within the field of AI, there's machine learning. And you know me, I like to be lazy, so I'm just going to say ML. And then within machine learning, there's a number of different subsets. You might have heard of something called deep learning, or neural nets, things like that. So deep learning and, so we're going to focus on machine learning. We'll get a little bit, well, I guess it depends on where I want to stop or where y'all want me to stop. We may get a little bit into deep learning and neural nets. But this is so you have a bigger picture of where machine learning falls in the spectrum of artificial intelligence. Okay, cool. So with that out of the way, there are two types of machine learning. The first is supervised. So it's basically like you are looking over the shoulder of the machine program. But in this, the data has labels. And the second one is unsupervised. You probably know where this is going. I apologize if you can't read my writing, I write too fast. And in this one, the data does not have labels. So in this approach to machine learning, you have a data set where you know the labels, and you write an algorithm to take the existing data set and make predictions on new data. In the unsupervised situation, which is really fascinating, you basically are having a data set where you're like, I don't really know what the patterns are in this data set, and you're hoping that an algorithm can help suss you out. This is often done with clustering, where if you think about having like a bunch of data, I don't know, I'm just gonna draw a bunch of X's. Your algorithm might say, I've identified these 3 clusters of data, and then you can go in and kind of see what the patterns are between those different clusters. In supervised learning, you can either have a regression, which means you have a continuous output, or you can have a classification, which is a discrete valued output. Think like integers would be discrete versus continuous would be fractions, decimals, that sort of thing. So integers plus decimals. You can keep dividing a number all the way to infinite number of decimal points. So that would be a regression. Okay, so we are going to start with supervised learning because it's a lot easier. Yay! Okay, so the basic structure of supervised learning goes like this. You have a training set. And then you write a learning algorithm. So we're just going to box it, but LOL, both of these boxes are a lot of work. Your learning algorithm goes and makes a hypothesis, which I'm going to represent with H in a different color, because that is the output. And into H, we have to do some stuff. We have to give it data, or I guess we should say we have to give it new data. So in this, I'm just going to say X for now. And H spits out Y. So the reason why I'm using X and Y here is because if we draw our familiar two-dimensional axis, we have our independent variable on the horizontal axis, which we often represent with X, and we have our dependent variable on the vertical axis, which we often represent with Y. So in this situation, we have our H function, or it's labeled as a hypothesis function, which I think is kind of a funny name, but that's just what we call it. So we have our function H of X, and H of X depends on the values we give it. Just like a regular function, we give it a value of X, and it spits out a value of Y. So in other words, it maps our input to an output. So how do we represent this function? Well, if we have a linear regression, or we have a linear regression with only one variable, then H of X is just a line, like I talked about in my intro video. Maybe the pattern between our data is just a line. So in that case, H of X can be represented. Let's move you up a little bit so I get more space. Okay, cool. So H of X can be represented just like this, AX plus B. We're in the machine learning world, so instead of A and B, we're going to use the terminology that Andrew Ng used, that data scientists use, and we're going to write this the other way around. So B is going to be first, and we're going to represent that with a theta 0 plus theta 1 x. This is the same equation. This is B, and this is A. We're just writing it a little bit different. So let's say I have some data. Let's say that we are plotting, we're creating a plot, we're not plotting to do something. Time practicing. Let's say you want to figure out how to become an expert piano player. So you gather a bunch of data about all of the expert piano players that you know of, and you plot the time that those folks spent practicing with their expertise. And let's say you get something that looks kind of like this. Maybe you have like a prodigy over here. Maybe you have someone that spent a lot of time but didn't get so good. So you could come in and say, yeah, this looks kind of like a line, which is what personally I would expect. Prodigies are very rare. I don't even know personally if they, well, whatever, we won't get into that. But the idea is that the more time you spend practicing on your instrument, the more of an expert you'll be, the more pieces you'll be able to play, the more technically proficient you will be. So our hypothesis function, our H of X function, can be represented with this line. And these are called our parameters. So depending on these parameters, we're going to get different shapes of the line. So for example, if theta naught is 0, then we have a line that goes through the origin, because this is it determines the y-intercept. Can you all see that? Okay, yeah. And if you have theta 1 equals 0, then you have, what do you think? What do you have if you have no slope? Okay, you have a flat line. So these two parameters can vary depending on what the input data is, and they will give us lines with different slopes. If there's no slope and that's flat, you're just walking on flat ground. If theta 1 is very large, you have a steep slope, you're running up a very steep hill. Okay, so now here comes the tricky question. How do we come up with these parameters so that we actually get a good result? Well, we kind of want to choose these so that h of x is close to the actual data values, the actual y values that we have in our training examples. So this is really a minimization issue. So we want to minimize theta naught and theta 1 and the difference between h and x. In other words, like I was talking about in the last video, we want to minimize the distance between these values. So this white line is our prediction, our hypotheses as to what pattern the actual data follows, and the x's are the actual data. And ideally, we want the distances between the sum, we want the sum of the distances between the actual and the predicted values to be as small as possible. So it's minimization. And so this is where we introduce what is called the cost function. And I'm totally out of space, so we are going to do this. Oops, okay. Okay, so the cost function has a shape like this. It depends on our two parameters. So we're going to divide by 1 over 2m, where m, let me just double check my notes because I didn't, yeah, it's the number of training examples. I didn't memorize that one. Training examples. So in this case, it would be the number of x's. Parentheses, x. And it's going to be the sum from I equals 1 to m. So we're going to sum over all of the training examples. And we are going to take the difference between the point on the line, or I should say a point on the line, and each of the y values for the x. So the way we represent that is h of theta of x I minus y I, and we're going to square that. Okay, so this is basically a squared error function. Why are we using the squared error function? Well, honestly, because it's a reasonable choice. It works well enough for what we want it to do. And it works particularly well for most regression problems. Other cost functions will work too, but this works well for most regressions. So this is kind of like an average difference. See, we're dividing by 1 over 2 of the 2 times the number of training examples. So it's average-ish. But it's slightly, I like the way that Andrew Ng calls this, it's slightly fancier than a standard average. So yeah, so this is the cost function, and the cost function will help us to find this minimum hypothesis function, or this minimum line or curve that is the best fit to our data. One quick note on notation, if you're like, what is this I doing here? That just tells us, if we were to sit here and label all of these data points, and I said, I'm going to get a different color. If I said this is 1, this is 2, this is 3, this is 4, 5, etc., I would just input that for I. So for example, the first value would be, we would take h of x1, where that is like this point right here on the line, and subtract it from minus y1, where it's this value here. And then we would just repeat that for all of the data points. X2, it's not squared, so let me put that in parentheses. It really just indicates, it helps you to keep track of like, I'm adding the difference between my hypothesis function and the actual function for each of these data points. And we'll do that 2 minus y of 2 plus, and then you do that for all of the data points. Okay, so the goal to find a best fit line is to minimize the cost function. Cool. Okay, so I'm going to leave it there for now because we've covered a lot already, and we will get into how to minimize the cost function in the next video. Yay! All right, please let me know if you have any questions. I put down my handy dandy notebook. Thank you very much for watching, and we'll see you next time. Bye!